Welcome to Limitless Math. Today we're diving into angle bisectors, a fundamental concept in geometry that you'll see on the SAT, ACT, and in your math courses. An angle bisector is simply a ray that divides an angle into two equal parts. Let's start with our first example. Here's a problem you might see on an exam. Identify which ray bisects the given angle. We have angle AOB measuring 120 degrees. We need to find which ray bisects this angle into two equal parts. Ray C divides the 120-degree angle into two equal parts. Each part measures 60 degrees. This makes ray C the angle bisector. Example 2. If ray BD bisects angle ABC and angle ABD measures 35 degrees, what is the measure of angle ABC? Here's our setup. Ray BD bisects angle ABC, and we know that angle ABD measures 35 degrees. Since BD is an angle bisector, it divides angle ABC into two equal parts. If angle ABD is 35 degrees, then angle DBC must also be 35 degrees. Therefore, angle ABC equals angle ABD plus angle DBC, which is 35 degrees plus 35 degrees, giving us 70 degrees total. Example 3 introduces the angle bisector theorem. Any point on an angle bisector is equidistant from the two sides of the angle. Here we have an angle with its bisector. According to the theorem, if we pick any point on this bisector, it will be the same distance from both sides of the angle. Point Q lies on the angle bisector. The perpendicular distances from Q to both sides of the angle are equal. This property makes angle bisectors incredibly useful in geometry and real-world applications. Our final example shows how angle bisectors appear in real life. Imagine you're designing a triangular garden and want to place a fountain equidistant from two garden paths. We have two garden paths meeting at an angle. To place the fountain equidistant from both paths, we need to find the angle bisector. The angle bisector shows us exactly where to place the fountain. Any point along this line will be equidistant from both garden paths, ensuring the fountain is perfectly positioned. This demonstrates the practical power of angle bisectors in design, architecture, and engineering. Understanding these concepts will help you excel in geometry and see mathematics in the world around you. Perpendicular lines are fundamental in geometry and coordinate math. They're simply lines that intersect at exactly 90 degrees, forming perfect right angles. Example 1. Let's identify perpendicular lines visually. Here we have two lines intersecting. Notice the four angles formed at the intersection. Each angle measures exactly 90 degrees, making these lines perpendicular. Example 2. In coordinate geometry, perpendicular lines have a special slope relationship. Let's check if two lines are perpendicular using their slopes. Step 1. Identify the slopes. Line 1 has slope m1 equals 2. Line 2 has slope m2 equals negative 1/2. Step 2. Check if m1 times m2 equals negative 1. 2 times negative 1/2 equals negative 1. Since this is true, the lines are perpendicular. Example 3. Now let's find the equation of a line perpendicular to a given line and passing through a specific point. Step 1. The given line has slope 3, so the perpendicular line must have slope negative 1/3, since 3 times negative 1/3 equals negative 1. Step 2. Use point-slope form with our point 6, 1 and slope negative 1/3 to find the equation. Step 3. Simplify to get the final equation. The perpendicular line is y equals negative 1/3 x plus 3. Example 4. Real-world application. In architecture, perpendicular lines ensure structural integrity. Let's check if wall supports are properly perpendicular. For perpendicular support, we need the negative reciprocal of 0.75. Since 0.75 equals 3/4, the perpendicular slope is negative 4/3. This ensures the support beam is exactly perpendicular to the wall beam, providing maximum structural strength and stability in construction. Remember the key relationship. Perpendicular lines have slopes that are negative reciprocals, where m1 times m2 equals negative 1. The angle bisector theorem is a fundamental concept in geometry that helps us understand the special properties of angle bisectors. This theorem states that any point on the angle bisector is equidistant from the two sides of the angle. Example 1. Let's start with a simple demonstration. Here we have angle ABC with its angle bisector BD. We'll show that any point P on this bisector is equidistant from the two sides of the angle. Now let's place a point P on the angle bisector and measure its distances to both sides of the angle. The perpendicular distance from P to side BA and the perpendicular distance from P to side BC should be equal. Example 2. Now let's explore the converse of the theorem. If a point is equidistant from two sides of an angle, then it must lie on the angle bisector. Here's a problem. Point Q is 4 units from both sides of angle XYZ. Does Q lie on the angle bisector? Step 1. We place point Q somewhere in the angle and verify that it's exactly 4 units from both sides. We draw perpendicular lines from Q to each side and measure the distances. Step 2. Since Q is equidistant from both sides, by the converse of the angle bisector theorem, point Q must lie on the angle bisector. Let's draw the angle bisector to verify this. Example 3. Now let's solve a more challenging problem. In triangle ABC, BD is the angle bisector of angle B. If the distance from point P on BD to side AB is 3x plus 2, and the distance to side BC is 5x minus 4, find the value of x. Step 1. By the angle bisector theorem, since P lies on the angle bisector, the distances from P to both sides must be equal. So we can set up the equation. 3x plus 2 equals 5x minus 4. Step 2. Now we solve for x. First, subtract 3x from both sides to get 2 equals 2x minus 4. Then add 4 to both sides to get 6 equals 2x. Finally, divide by 2 to get x equals 3. Example 4. Real-world application. An architect is designing a triangular garden with a fountain at the center. The fountain needs to be equidistant from all 3 sides of the garden. Where should the fountain be placed, and how does the angle bisector theorem help us solve this? Step 1. The solution is to find the incenter of the triangle, the point where all 3 angle bisectors meet. This point is equidistant from all 3 sides. Let's draw the angle bisectors from each vertex. Step 2. The incenter is where all 3 angle bisectors intersect. This is the perfect location for the fountain because, by the angle bisector theorem, this point is equidistant from all 3 sides of the garden. The angle bisector theorem and its converse are powerful tools in geometry. Remember, any point on an angle bisector is equidistant from the 2 sides, and conversely, any point equidistant from 2 sides lies on the angle bisector. These concepts help us solve problems in coordinate geometry, triangle properties, and real-world applications like architectural design. The perpendicular bisector theorem is a fundamental concept in geometry that helps us understand the special properties of perpendicular bisectors. This theorem has practical applications in construction, engineering, and design. First, let's understand what a perpendicular bisector is. A perpendicular bisector is a line that passes through the midpoint of a segment and forms a 90-degree angle with that segment. Example 1. Here's our first problem. We have a line L that is the perpendicular bisector of segment PQ, and point R lies on line L. We need to determine what we can conclude about the distances PR and QR. Let's visualize this problem. We have segment PQ with its perpendicular bisector line L. Point R lies somewhere on line L. Step 1. Apply the perpendicular bisector theorem. Since point R lies on the perpendicular bisector of segment PQ, the theorem tells us that R is equidistant from points P and Q. Example 2. Now we'll work with coordinates. We have points A at 2, 1 and B at 6, 5. Point C lies on the perpendicular bisector of segment AB, and we know C has coordinates x, 7. We need to find the value of x. Step 1. We apply the perpendicular bisector theorem. Since point C lies on the perpendicular bisector of segment AB, we know that CA equals CB. Step 2. We set up the distance equation using the distance formula. The distance from C to A equals the distance from C to B. This gives us the square root of x minus 2 squared plus 7 minus 1 squared equals the square root of x minus 6 squared plus 7 minus 5 squared. Simplifying the constants, we get the square root of x minus 2 squared plus 36 equals the square root of x minus 6 squared plus 4. Step 3. We square both sides to eliminate the square roots. This gives us x minus 2 squared plus 36 equals x minus 6 squared plus 4. Expanding both sides, x squared minus 4x plus 4 plus 36 equals x squared minus 12x plus 36 plus 4. The x squared terms cancel out, and simplifying gives us 8x equals 0, so x equals 0. Therefore, point C has coordinates 0, 7. Example 3. Here's a more challenging problem involving triangles. In triangle ABC, the perpendicular bisector of side AB passes through vertex C. We're given that AB equals 10 and AC equals 8. We need to find the length of BC. Let's visualize this triangle. We have triangle ABC where the perpendicular bisector of side AB passes through vertex C. This is a special configuration. The key insight is that since point C lies on the perpendicular bisector of segment AB, we can apply the perpendicular bisector theorem. This tells us that CA equals CB. Therefore, since CA equals CB and we know AC equals 8, we can conclude that BC also equals 8. This makes triangle ABC isosceles. Example 4. Now let's see how the perpendicular bisector theorem applies to real-world engineering. Engineers are building a suspension bridge with two support towers that are 800 meters apart. They need to position a cable anchor point so that it's equidistant from both towers. Where should this anchor point be placed? Here's our bridge setup. We have two towers 800 meters apart. The question is, where can we place the anchor point so it's equidistant from both towers? The answer comes from the perpendicular bisector theorem. Any point on the perpendicular bisector of the line segment connecting the two towers will be equidistant from both towers. The solution is to place the anchor point anywhere on the perpendicular bisector of the line segment connecting the two towers. This ensures the anchor point is exactly equidistant from both towers, which is crucial for the structural integrity and balance of the suspension bridge. Example 1. Constructing an angle bisector for a simple acute angle. Here we have angle AOB measuring 60 degrees. Our goal is to find the ray that divides this angle into two equal 30-degree angles. Step 1. Place your compass point at the vertex O. Draw an arc that intersects both rays of the angle. This arc should have any convenient radius. Let's use about 2 units. Step 2. Now place your compass at point P and draw an arc in the interior of the angle. Keep the same compass width. This is crucial for accuracy. Step 3. Without changing the compass width, place the compass at point Q and draw another arc. This arc should intersect the previous arc at a point inside the angle. Step 4. Draw a ray from the vertex O through point R. This ray is the angle bisector, dividing the original 60-degree angle into two equal 30-degree angles. Example 2. Constructing an angle bisector for an obtuse angle. Here we have angle COD measuring 120 degrees. The construction method is identical, but notice how the angle bisector creates two 60-degree angles. Following the same steps, first, place the compass at vertex O and draw an arc intersecting both rays. The key insight is that this method works for any angle size. Example 3. Multi-step construction with measurement verification. We'll construct an angle bisector and then verify our work by measuring both resulting angles to ensure they're equal. Step 1. Construct the angle bisector using our standard method. Place compass at O, draw the initial arc, then create the intersecting arcs to find the bisector point. Step 2. Verification. We can measure each resulting angle to confirm they're equal. Both angles should measure approximately 22.5 degrees, proving our construction is accurate. Example 4. Real-world application in architectural design. Architects use angle bisectors when designing roof trusses to ensure equal load distribution. Here's a roof truss where we need to find the center support beam. Using our angle bisector construction, we can find the exact center line for the support beam. This ensures the roof load is distributed equally to both walls, critical for structural integrity. This construction method ensures perfect symmetry and optimal load distribution. The same principle applies in bridge design, furniture making, and any application requiring precise angle division. While compass and straight-edge construction teaches us the fundamental principles, modern digital tools like GeoGebra, AutoCAD, and other geometry software can perform these constructions with perfect precision automatically. However, understanding the manual process helps you verify digital results and builds deeper geometric intuition. Example 1. Construct a perpendicular line at point P on line AB. This is the most basic perpendicular construction and forms the foundation for all other perpendicular constructions. Step 1. Place your compass point at P and draw an arc that intersects the line at 2 points. Make sure the arc radius is large enough to create clear intersection points on both sides of P. Step 2. Now place your compass at point C and draw an arc above the line. Keep the same compass width. This is crucial for accuracy. Step 3. Without changing your compass width, place it at point D and draw another arc above the line. The intersection of these two arcs will give us our key point. Step 4. Draw a line from point E through point P. This line is perpendicular to line AB at point P. The construction works because we created two congruent triangles. Example 2. Construct a perpendicular from external point Q to line AB. This construction is slightly more complex but uses the same fundamental principles. Step 1. From point Q, draw an arc large enough to intersect line AB at 2 points. The arc should be centered at Q with a radius that clearly crosses the line. Step 2. Place your compass at R and draw an arc below the line. Then place it at S and draw another arc below the line with the same radius. These arcs will intersect. Step 3. Draw a line from Q through T. This line is perpendicular to AB. Mark the intersection point where this perpendicular meets line AB. Example 3. Construct the perpendicular bisector of line segment CD. This construction combines finding the midpoint with creating a perpendicular line. Step 1. Place your compass at C and draw an arc with radius greater than half the length of CD. This arc should extend both above and below the line segment. Step 2. Keep the same compass width and place it at D. Draw another arc that intersects the first arc at 2 points, one above and one below the line segment. Step 3. Draw a line through points P and Q. This line is the perpendicular bisector of CD. It passes through the midpoint and is perpendicular to the segment. Example 4. Real-world application. An architect needs to ensure a support beam is perfectly perpendicular to the foundation wall. Using compass and straight-edge construction ensures mathematical precision. Using our perpendicular construction method. First, we create arcs from the attachment point to establish reference points on the foundation wall. Next, we create intersecting arcs from these reference points to find the precise perpendicular direction for our support beam. Finally, we draw the support beam along this perpendicular line. This mathematical construction ensures the beam is exactly 90 degrees to the foundation, providing optimal structural support. Modern software tools like CAD programs can automate these constructions with perfect precision, but understanding the geometric principles ensures you can verify accuracy and troubleshoot when needed. Example 1. Architecture and building design. In construction, angle bisectors help create perfectly symmetrical roof lines and corner angles. Let's see how architects use this mathematical principle. The angle bisector divides the roof angle into 2 equal parts, ensuring the building is perfectly symmetrical. This creates structural balance and aesthetic appeal. Example 2. Bridge engineering. Perpendicular lines are crucial in bridge construction. Support beams must be perfectly perpendicular to the bridge deck to distribute weight evenly and ensure structural integrity. Notice the 90-degree angles where each support meets the bridge deck. This perpendicular relationship ensures maximum load-bearing capacity and prevents the bridge from collapsing under weight. Example 3. GPS navigation systems. GPS uses angle bisector algorithms to determine your exact location. When your phone receives signals from multiple satellites, it uses geometric principles to triangulate your position. The GPS system draws lines from each satellite to your phone, creating angles. Angle bisectors help calculate the most accurate position by finding the point equidistant from multiple signal sources. Example 4. Medical imaging technology. CT scans use perpendicular lines and angle bisectors to reconstruct 3D images of the human body. This is one of the most advanced applications of geometric principles in modern medicine. X-ray beams pass through the body at perpendicular angles from multiple directions. The computer uses angle bisector calculations to determine where tissues of different densities are located, creating detailed cross-sectional images. This mathematical precision allows doctors to see inside the human body without surgery, saving countless lives through early diagnosis and treatment planning. Geometry literally helps save lives in modern medicine. Let's examine the most common mistakes students make when working with angle bisectors and perpendicular lines. Here's a typical problem where a student confuses an angle bisector with a perpendicular bisector. The problem asks, draw the angle bisector of angle ABC. But watch what this student does incorrectly. Instead of bisecting the angle, the student draws a perpendicular bisector of segment AC. This is completely wrong. The perpendicular bisector divides a line segment, not an angle. Now let's see the correct solution. An angle bisector divides the angle into two equal parts. We need to find the ray from B that splits angle ABC in half. Key tip: remember that angle bisectors divide angles, while perpendicular bisectors divide line segments. Always identify what you're bisecting before you start. Here's another common mistake in angle bisector construction. Students often make errors with their compass measurements, leading to inaccurate bisectors. Step 1 in construction requires equal radius arcs from the vertex, but this student uses different radii, creating unequal distances from point E. This leads to an incorrect angle bisector because the construction method requires equal distances from the vertex. Let's see the correct approach. Essential tip for constructions: always use the same compass setting for both arcs when constructing angle bisectors. Precision in measurement leads to accurate results. Now let's examine a more complex scenario with multiple errors in perpendicular line construction. This student makes several mistakes that compound the problem. Error number 1, point M is not at the midpoint of PQ. For a perpendicular bisector, M should be exactly halfway between P and Q. Error number 2, the student uses unequal arc radii from points P and Q. This creates intersection points that won't form a true perpendicular. Now let's fix all these errors step by step. First, we place M at the true midpoint of PQ. Then we use equal radii from both P and Q to create proper intersection points. Critical tip: when constructing perpendiculars, verify your work by measuring. The perpendicular should form 4 right angles with the baseline. Our final example shows how to use dynamic geometry software to verify your constructions and avoid errors. This is essential for exam prep and real-world applications. Step 1. Input your construction into the software. The program will show exact measurements and highlight any errors in your work. Step 2. The software confirms our angle bisector is correct because both resulting angles measure exactly 33.7 degrees. This precision verification is impossible with hand measurements alone. Professional tip: always use technology to verify your constructions, especially for important exams like the SAT, ACT, or AP tests. Software like GeoGebra, Desmos, or even graphing calculators can catch errors that visual inspection might miss. Remember these key strategies: distinguish between angle bisectors and perpendicular bisectors, use precise compass measurements, verify your constructions, and leverage technology for accuracy. These tips will help you master geometric constructions and excel in your math studies.